Hello everyone, I'm going to give a presentation on outcomes of the research carried from the project Model Development and Analysis of Flash Boiling Spray for Internal Combustion Engines. This project is funded by SERB under Early Career Research Award for Dr. Kaushik Saha. My name is Akhil and I am one of the PhD student working with Dr. Kaushik Saha in this project. The objective of these projects are primarily achieved by two ways. One is through experimental techniques. More details regarding this will be explained by my colleague Anurag, who is also involved in this project, and I will be taking you through the numerical model development point of view. With that said, let's begin. This is the outline of this presentation. Initially, I'll be discussing about the different methodologies of the fuel injection in an SI engine and followed with the spray simulations carried under non-flashing conditions and its validation with the experimental studies. Then I'll introduce to an interesting topic called flash boiling and how it is relevant to IC engines we will be discussing. Then how we develop a model which consider the vaporization effects of the flash boiling spray. Finally, the obtained results are also validated with the experimental studies. Primarily, there are two different fuel injection methodologies under SI engine. One is a conventional port fuel injection, where the fuel is injected in the intake port of the engine, which it mixes with the incoming air uh, to form a combustible mixture, as shown in the top image. The other methodology is the gasoline direct injection, which the fuel will be injected directly into the combustion chamber or engine cylinder, just like how is diesel is injected in a CI engine case. By doing so, the engine volumetric efficiency may increase up to 10% and the compression ratio about 1.5% compared with the PFI. There are two major reasons behind this. One, there is no fuel mixing with the air which is incoming to the intake port. By this, the amount of volume occupied by the fuel during the suction stroke with the incoming air in the PFI is eliminated in the which is eliminated in the GDA system, which means more amount of air intake is happening so that we can inject more fuel to accommodate the stoichiometric combustion. So the overall volumetric efficiency increases. Another thing to note here is we inject fuel directly into the combustion chamber. Due to the spray breakup and formation of small droplets in the GDA system, charge cooling effect is observed, which means these tiny droplets will consume the surrounding energy to get vaporized and make the local condition cooler. If the local conditions are cooled down a bit, when we intake more air and compress the charge easily without bothering about the auto ignition. Thus, the GDI will also allow an engine to achieve high compression ratio than the PFI system. In this project, the spray simulations have been carried out by using the ROI approach. Through the experimental studies, the rate of injection profile is obtained where the depending on the injection duration, the needle lift of an injector is recorded. Based on the obtained profile, the spray parcels are injected into the combustion chamber. Here in numerical simulations, a group of droplets which have similar size are called as parcels, and the blob injection approach is considered. It means the injected droplet size is equal to the size of the nozzle hole geometry. For ROI based simulation, spray cone angle, injected mass, nozzle position, nozzle diameter, plume targeting angle, these are all needed and which are all considered as the input parameters. Consideration of hole-to-hole fuel flow fluctuations and flow inside the fuel injector is not possible in an ROI-based approach, which is one of the limitation of this kind of a phenomenon. In this project, for numerical simulations, we considered the spray-G injector from the engine combustion network, which is developed by Delphi Corporation. Obtaining the injected geometrical details is quite challenging as it is a proprietary thing for the injector manufacturers. From the ECN, one can obtain the spray-G GDI injector geometrical details to perform the numerical simulations and experimental studies. ECN is an international collaboration among the experimental and computational researchers in engine combustion. This slide shows the operating conditions of the spray G injector. The difference between the standard and flash boiling conditions are seen in the chamber are seen at the chamber temperature and chamber pressure conditions. Under flash boiling, the liquid will be superheated and it will rapidly vaporizes. More about the flash boiling will be discussed in the coming slides. The spray simulation setup overview is as follows. This work is carried out using the Converge version 2.4 CFD code, and the spray is injected into a constant volume chamber of dimensions 108 by 108 mm. The maximum grid size is considered as 1 mm and the minimum grid size based on the embedding and AMR is obtained as 1.125 mm. The majority of the simulations were carried out using the RNG K-epsilon turbulence model. Few simulations in this non-flashing case is also carried out by using the standard K-epsilon and LDS turbulence model. The spray breakup is modeled using the KHRT model, droplet vaporization by the Frosling equation. From the literature, it has been observed that most of the spray simulations were carried out considering the standard K epsilon as the turbulence closure, where the turbulence constant C epsilon 1 is tuned to match the experimental data. The higher the C epsilon 1 value, the radiative pressure of the spray is reduced so that the spray will travel more distance. It also observed that the spray cone angle is also considered as one of the tuning parameter to match the experimental data. However, when coming to IC engine combustion simulation, RNG K epsilon and LES models are typically used, where in spray modeling, standard K epsilon is used most by the researchers. Unlike standard K epsilon, the RNG K epsilon model accounts for the low, medium, and high strain rates in the flow. So, in this work, we are restricting to RNG K epsilon model, and we will be exploring how we can get desired results so that there is no disturbance between the spray modeling and the combustion modeling. To maintain the consistency in this work, a new approach is carried out by varying the spray model constant, such as KH breakup time constant and the RT length constant. The KH breakup time is given as follows, in which the sigma KH and omega KH are the wavelength and the fastest wavelength growth rate of the KH instabilities. RP is the parcel radius and B1 is the tunable constant. B1 it has also introduced in order to account for the effects of the inner nozzle flow and breakup time that cannot be resolved directly. The higher the B1 value, the slower the breakup process. B1 varies from the injector to injector and it ranges from 1.73 to 60. This slide shows the effect of CBL on spray shape. On increasing the CBL, the spray width increases and parcel radius increases, and hence overall spray shape, spray penetration is decreases. To finalize the model constants of the spray G injector, parametric studies have been carried out. In this work, the parametric studies have been carried out where the values of B1 is equal to the 2 times of the CBL value. By varying those values, we have done the parametric studies. What actually these values signifies is the CBL value is the breakup length, which signifies the breakup length, where within the breakup length range, only KH instabilities or KH model is responsible for the spray breakup. After the spray breakup length range, both KH and RT models are activated, and whichever has the fastest wave growth rate, the code will allow it to be responsible for the spray breakup. From these parametric studies, it has been observed that the B1 as 32 and CBL 16 gave the close match to the liquid and the vapor penetration. The rightmost graph shows the comparison between the standard RNG and LES results, where the standard K epsilon model has turbulence model constant C epsilon 1 as 1.44, where the RNG and LES both has dynamic structure has the B1 and CBL value as 2.5 and 2.5. This slide shows the comparison of the spray shape in terms of parcel radius at 1 millisecond duration and the 2 millisecond duration. Here our fuel injection period is at 0.78 millisecond. At 2 millisecond downstream of the spray plume, majority of the spray parcels are sub-micron in size, which is extremely difficult to detect their presence using the experimental techniques like Mie scattering. In an experimental techniques, in order to effectively capture the smallest droplets in sprays, the droplet size should be comparable to or greater than the wavelength of the incoming light source. So it is highly not possible to capture the smallest droplet size of 2 micron level by using the experimental techniques. Such an observation where the droplet size is below 2 micron is not reported in the literature prior to this work. Next, we try to validate the obtained results from this approach in terms of suction velocity along the injector axis during the spray injection. There are two things where the negative velocity meant the plume merged and the gas flow was moving up towards the injector tip, and the positive values indicate that after the plume merging, plume collapse stage has arrived. So all the all the unsteady runs and the LES turbulence model which are tested for the comparison with the data for spray penetrations are also compared with the axial velocity data obtained from the experimental, and the results are presented in this slide. The measurements of the axial velocity were taken at a distance of 15 mm downstream of the injector tip and on the injector axis. The predictions using the standard capsule turbulence model does not hold good qualitatively and quantitatively compared with the predictions using the RNG capsule and the LES results. The best agreement comes with the prediction of the RNG capsule turbulence model, and there are non-monotonic slope changes after the zero 0.6 millisecond, as it is also seen from the experimental data also. The predictions using the LES turbulence models overlap throughout the duration of the simulation time, and they also exhibit slightly non-monotonic trend after zero 0.6 millisecond. However, the prediction with the LES model do not do a better job compared with the RNG capsular model. This is unusual since the prediction of the LES turbulence modeling approaches are supposed to be more realistic compared with the unsteady RANS approaches. This indicates that there is a room for further improvement using the LES turbulence modeling approaches, which constitute a scope for the future work. This slide shows the effect of stepped hole geometry on a RI-based spray simulation. A typical RI-based spray simulation, there is no hole geometry involved, and the spray injection is modeled as a point injection. However, it would be interesting to see how the spray characteristic would change if these point injection were initiated at the exit of the smaller hole, where the spray parcels would have to pass through the counterbore region before entering into the combustion chamber. The figure here on the right hand side represents the density variation of the gas mixture at a 0.8 millisecond on a vertical plane cutting through the midsection of the injector location, and the bottom one shows the horizontal plane provide the impression of the spray patternation and provide the insight of the extent of plume to plume interaction. Going through the results from the left to right, it is evident that how the local fluctuation increases as the dampening effect due to the higher turbulent viscosity decreases. In fact, the results including the stepped hole bear a proof of higher turbulent fluctuation. The presence of the stepped hole leads to additional disturbances at the point of the injection, which is manifested at the in the fluctuation even at the location of the tip of the spray plumes. Similar variations have also reported in the temperature contour. This slide shows the animation of the density variation during the spray injection on a vertical cut section of the two opposite plumes. The left one is without the stepped hole geometry, and the right one is with stepped hole geometry in a ROI-based spray simulation. Further, spray simulations have been carried out by using the blends of the gasoline, ethanol, and methanol combined together. Recently, Indian government is promoting Indian automotive manufacturers to develop and build the engines which are capable of running using the flex fuel, which means the engine can run up to 85% of ethanol and 15% of the gasoline. These flex fuel vehicles has much success in Brazil and US. However, in India, ethanol manufacturing cost is higher than the Brazil, which has a better production to consumption ratio than the others. In the place where ethanol is costlier, the alternative such as methanol can be looked into as an alternative. In China, recently, nearly 8% of the gasoline requirement in the transportation sector is replaced by the methanol within a concise period. NITI has also recommended methanol as a futuristic engine in its methanol economy program. This slide shows the fuel properties of ethanol, methanol, and isooctane, where the air fuel ratio of the E85 G18 fuel is 9.7. Hence, the blends are formulated in such a way that the air fuel ratio of the respective blends is similar to that of the E85 fuel. Moreover, experimental investigations were carried out on IC engines using the GEM fuel, but it is on a PFI engine, not on the GDI engine. Literature on the utilization of the GEM fuels using the GDI engines is still limited. As mentioned earlier, GDI engines have better volumetric efficiency and can go higher compression ratio. Hence, we would like to see the effect of the GEM blends on GDI system throughout this work. All the model parameters which are used for the spray G simulation were considered same for this study as well. This slide shows the liquid and vapor penetration of multiple blends, which are compared with the results obtained from the isooctane spray. It shows that all the sprays have performed similar to that of the isooctane sprays. However, the difference between among these have been observed in the cut section of the horizontal and where the vertical cut section of the spray plumes, which has been shown in the next slide. Here, multiple cut sections were considered at different locations. As we shown earlier, that the alcohol fuels have a high latent heat. Due to the latent heat differences, the local cooling of the air fuel mixture by 30 to 40 Kelvin is seen here between the isooctane and the E85 gasoline 15 case at different position perpendicular to the tip of the injector. An approximation of 10% change in the local density of the air fuel mixture is also observed in the work in this work at the same positions. The higher enthalpy of vaporization increases the charge cooling effect, and it will also allow engine to run at a high compression ratio, which eventually increases the efficiency of the engine. One of the significant advantage of the GDI engine over the PFI engine is the charge cooling effect, as mentioned earlier. In the PFI system, the charge mixture will be introduced during the suction stroke, and the end of the compression stroke, the temperature inside the cylinder will rise. The charge will auto-ignite and produce knock when the temperature reaches higher than the fuel flash point. However, when for a GDI engine, the charge cooling effect of the injected spray results in lower temperature at the end of the compression stroke. It allows the engine to run at higher compression ratios. Typically, it allows the GDI to operate a slightly higher compression ratios than the PFI engine. This suggests that binary and ternary fuels will help run the GDI engines even at higher compression ratios and perform better than the normal engine. Now let's discuss about a very interesting phenomena called flash boiling, which happens in a GDI engine. Flash boiling is a phenomenon. It happens when any liquid is subjected to its below saturation pressure conditions. It means when when a heated liquid fuel is injected into a chamber conditions where the chamber pressure is below its saturation pressure, then the liquid will undergo into superheated state known as flash boiling. GDI engines quite often run under part load conditions. Under such conditions, the pressure of the engine cylinder is subatmospheric, and the injector fuel temperature will be around 80 to 90 degrees Celsius, which are perfect conditions to achieve the flash boiling spray. The effects of the flash boiling spray has been explained and will be seen in the next slide. Let us assume the position A shown in the PT diagram is as the injected liquid temperature. When the heated liquid fuel is injected into a chamber pressure conditions below the saturation line, where B, which shown as B, then the liquid will undergo flash boiling. When the liquid is under such phenomena, it will try to reach the equilibrium position, which is shown as C. During this process, due to the internal superheating within a droplet, vapor bubbles will form, and such bubbles will activate as a nuclei. These vapor bubbles grow, and if the size of the bubbles is greater than the droplet size, it will erupt and break into small tiny droplets, which also called as the child droplets. The right image shows the breakup of the parent droplet when it is in the subcooled conditions and also in the superheated conditions. Thus, flash boiling enhances the spray breakup, and within no time, the parent droplet broken into multiple child droplets which have high surface area and are exposed to ambient conditions, and thus the vaporization rate also increases. Numerically, there are two ways to model the flash boiling spray. One by considering the bubble dynamics, which are where the bubble dynamics equation is coupled with the governing equations, and the other is by using the empirical coefficients. Firstly, we try to calculate the bubble growth by using the Rayleigh-Plessey equation under the superheated conditions, for which MATLAB code is written, and by using the ODE45 function. As shown in the graph, it has been observed that the bubble will grow from 0.1 micron to 1.4 microns in 1 microsecond under flash boiling conditions. This slide shows the typical time step size, which is approximately 1 microsecond, and the number of parcels injected during the spray simulation. Simulating a spray with a time step lower than the microsecond, which is coupled with additional bubble dynamics equation to consider the flashing effects, can be computationally very expensive. It may not be feasible or practically possible to apply such a method in an engine simulation where we need to solve the same equation for the several thousand parcels. To avoid this, we have formulated an expression based on the non-dimensional numbers, where the Jacob number and the pressure ratio, which signifies the flash boiling conditions. And the derived expression is as follows, where A and B are two tuning parameters. Jacob reference values are considered as at 300 Kelvin, except for the delta T in the Jacob number, where the delta T values are considered as the delta T obtained with the fuel injection temperature, which means the delta T in the numerator also cancels out the delta T in the denominator. In order to consider the superheating effects, we then multiply the Jacob formulation with the pressure ratio, which is defined as the pressure ratio is defined as the saturation pressure of the fuel divided by the chamber pressure. This equation is coupled with the existing Frost-Ling equation, which act as a subcooled vaporization, and the derived expression will taken care of the internal superheating. As seen in the earlier slides, the breakup phenomena of the flash boiling spray is different than the normal spray. Due to flashing, the child droplets have different sizes, which are much smaller than the subcooled spray child parcels. Also, from the experimental studies, it has been observed that there is a 40% reduction in droplet diameter of the flash boiling spray compared with the non-flashing spray. Generally, as shown here, R nu is equal to the constant B naught and the kh instability wavelength of sigma. B naught is a model constant which is usually used as a 0.61 by the most of the literature. Here we need to understand one thing, that the B naught as 0.61 is suggested based on the work done by Reitz on a diesel injector. The diesel injector is totally different than the gasoline injector. Liu et al. Has also suggested an equation to consider the B naught value depends on injector, which suggests that there is a scope in varying the B naught value. A smaller B naught value results in smaller drops from the breakup, vice versa. Coming to the RT model, the breakup time of Rayleigh-Taylor model is derived as CT divided by omega RT, and the wavelength is shown as a sigma RT is multiplied with the constant CRT. The CT is adjustable time constant, which has a typical value of 1, where CRT is a RT size constant, similar to B1 constant from the KH model. The CRT is also varied from injector to injector. It can be increased or decreased to change the predicted RT breakup droplet radius. Consider these, we have performed multiple simulations by varying each of the model constant. Slide shows the comparison of the spray shape, spray axial, and the radial penetration of the different simulations which have with the experimental spray image experimental spray DBA image. These images were taken at 0.5 in millisecond of the injection duration. Out of these three, the images shown on the right has a decent agreement with the experimental image. Even though they look similar, there is a subtle difference between them. This slide shows the effect of reducing the CT, where on reducing the spray is able to start a breakup much quicker than the normal conditions, which is clearly distinguishable in the zoom spray images. And this slide shows the comparison of the global SMD among different simulations. It is clear that there is a clear indication of reduction of spray SMD on reducing the spray constant values compared with the original values. This slide shows the local SMD predictions. The right hand side image shows the SMD at Sotomayor diameter variations at 15 mm downstream of the fuel injector along the axial distance. The SMD is measured by using the PDA techniques. The left hand side image shows the spray parcels at 14 to 16 mm distance. It has been observed that numerically predicted data is over predicting than the experimental. However, the values are within the acceptable range, where the numerical predicted values are within the range of 12 to 15 microns, whereas the experimental values are reported at 10 to 13 microns. Further, the developed model and the followed approach is validated with the density variations below the fuel injector at a distance of 2 mm. All these simulations shown here are simulated with the vaporization model constant of 2, and the experimental images is taken through the X-ray imaging techniques by the Sandia National Laboratory. It clearly shows that by using the developed vaporization model and by using the modified spray constant, the density variations are matching with the experimental data. By this, the developed model has been validated successfully with the experimental data in terms of spray shape, liquid penetration, and the local SMD and the local density variation. This slide shows the qualitative comparison of the experimental spray image taken in our lab under flash boiling conditions with the developed model spray image. From this also we can say that the developed model has been validated qualitatively with the experimental spray image. To summarize the highlights of this work, the spray simulations of the non-flashing spray have been carried out with a new breakup modeling approach, and the results obtained through this approach are successfully validated with the experimental data in terms of spray penetration, SMD, and the suction velocity. We developed a new flash boiling vaporization model which will not require humongous computational resources, and the new spray breakup approach is also for the followed for the flash boiling sprays. The obtained flashing results were validated with the experimental data in terms of spray shape, spray penetration, SMD, and the local density fluctuations successfully. These are the publications achieved through this project, out of which two journals are published and two are yet to be communicated, and four conferences papers were presented. We would like to acknowledge DST and SERB for funding this project, ECN for providing the geometrical details of the spray G injector and the experimental data, and finally PADAM HPC facility at the IIT Delhi for running the spray simulations. Thank you.